Hello and welcome back to Chemistry 2330, Introduction to Organics Chemistry. We're hitting the final stretch. And so what we want to do now is we want to finish strong, finish our homework, and do our last get our last exam grade, which is coming up on December 2nd. Get a really good grade for that. And then I'm going to give you some hints on studying for the final. Okay, it's going to be a top hat exam. It's going to be covering all 16 chapters, but the number 3 is just going to focus on 12, 13, 14, 15, and 16, and that's December 2nd. But the final will cover all 16 chapters about equally, and hopefully that will pick the major things that happen in each chapter, and those are the ones that we're going to remember as we move forward. If you move forward to the biochem course, hopefully you'll remember those things and be able to do that. If this is your final chemistry course, I hope that I had an impact on it in a positive way. All right, so due this week is, of course, we're doing chapter 15 today, enolates. It's another continuation on carbonyl compounds, and it's our last carbonyl chapter, and then we're gonna go off onto polymer chemistry for our last lectures that we have. We have our homework for chapter 15 is going to be due on Monday, November 23rd. That's the week of Thanksgiving. Okay, so if you plan to travel that week, please don't, or do a lot of self-isolating after you get back. And if you are, but get that in before you travel so that you can do that. Do a lot of social distancing, do a lot of iron line. My family, we're actually doing a Jackbox evening where we're going to have all 20 of us on Jackbox, and we're going to be doing that, and everybody's going to have their own little meals in their own little places for safety's sake. Okay. That being said, hopefully you'll stay well, and we'll be back for our final exam and our last exam and finish the season out strong. Okay, so there's nothing else due this week other than coming to class. And so we're going to go ahead and hit this enolate chapter, and then it'll take today and Wednesday to finish this out. But we should be able to do after that, start doing an idea of maybe I can do polymers in one chapter so that we can, on our review, I'm actually going to be posting the hot topics for chapters 1 through 16 on my Canvas site. So you'll see that coming up soon. Okay, so that being said, we got about 29 of us here. So let me go ahead and start sharing my screen. Yeah. So unfortunately, COVID numbers are going up, and so we need to probably double down on all our safety procedures for the next couple of months to get them to come down. Okay, so I said before that we started these last set of chapters all about the carbonyl compounds. We started with the most simple ones, which were the aldehyde and the ketone. And so that gave us certain reactivities. We learned how to make them. We learned about how they react to form alcohols. Then we moved on to carboxylic acids and how just adding that OH group to that carbonyl changed its reactivity and made it a very acidic organic compound, and it had delocalization in it. But then we could take that carboxylic acid and take that OH off and put other electronegative atoms like chlorine or alcohols or nitrogens to there and make other derivatives. And from those other derivatives, we were able to go back and forth between the carboxylic acid salt all the way to the acid chloride and the anhydride, the ester, and the amide, and all the way back. So you have reactions for getting through all of those different things, remembering that reactivity is in order of the base strength of the leaving group. The better the base it is, i.e. the nitrogen, the less it reacts with other things. So draw that conclusion. Now, those are all the things we've learned about carbonyl so far. But we're going to use that same property of that double bond between carbon and oxygen, that partially positive carbon, to do a new set of reactions. Okay, so let's talk about not the carbonyl itself, but the two carbons next to it. Okay, so the two carbons next to it feel the influence of that partially positive charge on carbon. And because it does that, we call the we can actually change the acidity of the hydrogens nearby. Okay, so first of all, we started calling this when we took that cyclic esters and cyclic amides, we started using the alpha, beta, gamma terminology to say things that are adjacent to a carbonyl compound. We're going to use that same terminology to define different types of hydrogens and different locations on this set of carbonyl compounds. Okay, so the carbon right next to the carbonyl compound is what we call the alpha carbon. So it's basically the first carbon away from the carbonyl. The carbonyl is pulling electron density from it, making those carbons different than if they were just hydrocarbons. Okay, it makes them have less electronegativity, which means the hydrogens attached to them are what we call alpha hydrogens. So in this case, we have 2 alpha hydrogens. In this case, we have 3 alpha hydrogens. And these alpha hydrogens are more acidic than regular alkanes or alkenes. However, they are less acidic than the hydroxyl, the hydrogen on that hydroxyl unit. Okay, so that carbonyl is the reason they are more acidic. Okay, now if they are more acidic, then we can do some chemistry with them using base. Okay, so the key things here are we have some kind of carbonyl compound. The carbons next to them are called alpha carbons. And if we go 1 carbon over, that's the beta carbon. We go out 1 carbon over, that would be the gamma carbon. Alpha, beta, gamma, etc. So then we could name them all the way down there. But let's first look at that alpha carbon and more particularly the alpha hydrogens. Okay. So I said before that the whole reason those are more acidic is because that inductive effect between that carbonyl carbon being partially positive, pulling electron density through that carbon-carbon bond. The other thing that makes it more acidic is the fact that if you do pull that hydrogen off, what you end up with is the ability to share that charge with the oxygen here. Now, does this look familiar? It should look familiar because when we had carboxylic acids, that hydrogen on a carboxylic acid was more acidic because you could kick the electrons in here and have the charge up here and spread that negative charge out over 2 oxygens. That's what made that hydrogen more acidic. So now we have an electron withdrawing group helping us, and we have resonance stability, making those more acidic than regular sp3 hybridized carbons. Okay, do we see why these are more acidic? 2 reasons: inductive effect, and then that stabilization of the negative charge over more than 1 atom. In this case, 2 atoms, with the case of the oxygen being one of them and the carbon being the other. And it goes back and forth, back and forth. And in fact, this reaction tends to most of the time be at some kind of equilibrium. So we're going to see that again and again. Okay? Questions on that? Alpha hydrogens are the one next to the carbonyl. Those are more acidic because of delocalization and our electron withdrawing, inductive effect. So let's look at the acidity of these things and start with things we know. So we're going to start here at the bottom of the table. Okay, these are your normal sp3 hybridized hydrogens here. They are the least acidic of the most of the compounds we've worked with. Okay, so they are the least acidic, meaning that they are very strong bases. Okay, and then we knew that by changing from sp3 to sp2, they became a little more acidic. And changing to sp right here for the acetylene, they were even more acidic. And that was the most acidic hydrocarbon we had up to that time. Okay, so now we're introducing those alpha hydrogens. And those alpha hydrogens are more acidic because of those 2 effects. And therefore, just with having this carbonyl compound here, this hydrogen is more acidic than the alkynyl hydrogen. Okay, so that we can pull it off with something a little bit stronger than hydroxide. Now, if we had a ketone instead, that's even a little more acidic. Okay, why? The reason it is more acidic is that then this just comparing these two, the reason it's more acidic here is, notice there is an oxygen right here. And notice in this one, there's a carbon, okay? So that means this oxygen can donate a little bit of electron density to the carbonyl, making it less inductively withdrawing from that hydrogen. Therefore, this hydrogen is not as acidic as this hydrogen because of that oxygen there. Pay attention to that. Having that oxygen on that carbonyl lowers the acidity. We're going to see that again in just a minute. Now, by removing that oxygen, and so it's kind of not donating or withdrawing, that's where we get the natural its acidity just from the carbonyl, just from that delocalization, and that gives us that number about 20. Okay, then water and alcohol are about the same as acidity goes. But now to increase the influence of that effect, what if we put 2 carbonyls on an alpha hydrogen, on an alpha carbon? If we put 2 carbonyls on an alpha carbon, that means we're going to have the effect being pulled away on both sides. So it should become more acidic. And we do see that, okay? When we have this right here, notice we have our ethyl oxide group here, meaning that this side's an ester and this side's an ester. So we call this a beta diester. Notice this is the carbonyl we talk about. This is the alpha position. That makes that the beta position. So this is a beta diester. But what it means is both of those carbonyls are tugging on that alpha carbon. That makes that alpha hydrogen more acidic. In fact, it's more acidic than the proton on water. So we are starting to be able to see we can remove these hydrogens with just things like hydroxide and alkoxides. Okay, so how can we make it even more acidic? Let's remove one of those oxygens, and I bet it gets more acidic. So if we do this right here, and we still have one of the esters, but now we switch it over so we have a ketone on the other side, and the acidity goes up, okay? So we only have one thing donating electron density to the carbonyl, and therefore, instead of the 2 we see down here, so it gets more acidic. And notice that makes us have a, this is our carbonyl compound, this is our alpha, this makes our beta. So this is a beta keto ester, the keto for the ketone and the ester for the ester. Okay, so having that other carbonyl group spaced one away makes that alpha carbon and that hydrogen on that alpha carbon more acidic. Okay. And if you remember, phenol is more acidic than alcohol, it's because it can delocalize the charge on the ring. What if we get rid of this last oxygen here and go to something else? So let's look at our last one here. We got rid of the oxygen, so we just have carbons right here. We have no donating groups, so the carbonyl gets to do all the electron withdrawing it can. And in that case, the acidity again goes up from this alpha hydrogen. And because we have this ketone at this site and at the beta site, because this is our alpha site, we have a beta diketone. So in this set, the beta diketone is the most acidic alpha hydrogen you can find, and it's the one right in between the 2 ketones. Okay, do we see what an alpha hydrogen is, why it's acidic, and why it keeps increasing in acidity based on how many carbonyls and how much electron withdrawing they can do? Response, thumbs up, something. Type hello in the chat room if you're alive. Okay, there we go. Somebody said it. All right, I can keep teaching now. All right. So what happens when we remove one of those? Great, great. Yes, thank you for participating. I got to keep asking questions. All right. All right. Okay. Enolate ions. So if we have a proton on one of these alpha carbons and we remove it, we create an ion. Okay. And that ion has that stabilized over two atoms. It's stabilized on a carbon and it's stabilized on an oxygen. Okay. We can make that by two different methods. We can either do it quantitatively, which means we use a very strong base and it's not reversible. So the arrow only goes in one direction. Okay. So this is like what we would do with acetylene. We would use that sodium amide on acetylene to completely deprotonate it and turn it into a nucleophile. Okay. So we can do that too with a very strong base, and it would generate our enolate anion. Okay. Now, you may have heard me say turn it into a nucleophile. Well, we just turned our ketone compound into a nucleophile. So we're going to use it as a nucleophile when we have that. Okay. If we have a more acidic one, like a beta diketone here, we can use a weaker base like sodium hydroxide and actually turn it into, notice it's not in equilibrium, it's converting completely to the enolate ion, and then water. Water's such a weak acid, it can't protonate this weaker base, and therefore it goes all the way to its quantitative state. It goes all the way to the enolate. Okay, so it always goes by acid-base strength. So you always go from stronger acid, stronger base to weaker acid, weaker base. And the bigger the difference, greater than about 5 pH points, is the more likely to be completely one or the other. And once you get in close together, they start forming equilibriums. Okay, so now that we formed this negative charge, now that negative charge can act as a nucleophile. Okay, so in this case here, we were able to deprotonate one of these ketone carbon compounds. And now that lone pair can come in and attack as a nucleophile to generate our addition product. Okay, notice this still has a charge on it because our addition product has not been acidified yet. Okay, so we form our nucleophile and then it forms our charged species. And then we have to, at the end of the reaction, add something like water if it's really acidic, or occasionally you have to add acid if it's not acidic enough. Okay, so the idea here is that once you form that, then you're going to somehow lose a group, either protonate that to give you an alcohol, or in the case of an ester, you can actually have the formation of your tetrahedral intermediate, but we have a really good leaving group. We have that alkoxide as a leaving group. And so because that's a good leaving group, we actually end up with a dicarbonyl compound. Okay. So over here, we didn't have a good leaving group. R- is a bad leaving group, so it stops at the addition product. Here, we're going to show you a couple different reactions that have these good leaving groups, and therefore they regenerate a carbonyl. So we have two sets of reactions, one where they form the addition product only, and then one where they have a good leaving group. And when you form the addition product only, now you have when you acidify, you'll have a alcohol that can do other chemistry. So let's talk about just that base system first. Okay, so once we deprotonate our carbonyl compound at that alpha carbon, it turns it into a nucleophile, and then our nucleophile reacts with other carbonyls. Okay, so the first reaction I want to talk about is called the aldol. And you can think about it, aldols always produce an alcohol, okay? First in their first step, aldol alcohol, okay? The other thing about an aldol reaction is it's an aldehyde or a ketone, okay? So write that down. Aldol is with an aldehyde or a ketone, and it produces an OH group at the end of the reaction. Okay, so that's the key here. Aldol reaction, aldehyde ketone produces an alcohol. Okay, so let's look at that. Okay, so let's look at this carbonyl compound here. And let's see, we have a carbonyl compound. Oh, look, there's no alpha hydrogen on this side because we don't have an alpha carbon. Okay, there's no alpha carbon there. So that means we have to remove the hydrogen from this side. Okay, we see that how there's no alpha carbon, so you can't, that is not an alpha hydrogen, that's actually the carbonyl hydrogen. So this is not removed here. So that is not going to react. So that means that when we form this anion, it's going to form on this side here. And when we form that anion, it's going to attack a carbonyl. Okay, so that's how we do it with an aldehyde. You only have one side of that can react. Let's look at the ketone. If we look at the ketone, we can remove an alpha hydrogen from this side or this side. In this case, it's symmetrical, so it'll give us the same product. And once we form that, it's going to attack the carbonyl. And the carbonyl that was attacked is the one that's going to give you the OH group. The carbonyl that is still a carbonyl is the molecule you made the enolate with. Notice that the enolate ion opens up your carbon-oxygen double bond to give you that alkoxide first, the salt of alcohol, and then it gives you, after protonation, an alcohol. Okay, so that means aldehydes, if you do just an aldol reaction and you have two equivalents of your aldehyde, it will always give you a beta hydroxy aldehyde. Okay, and if you have two equivalents of a ketone, it will always give you a beta hydroxy ketone. Okay, so let's look at that a little deeper. Okay, why does it do that? Okay, well, the first step in an aldol reaction is the removing of one of those alpha hydrogens to create our enolate ion. Okay, so let's look at that. So in this case, we have an aldehyde, and we're going to use equilibrium conditions. Okay, so hydroxide is, not as basic as the enolate ion, but they're pretty close. So what we end up doing is doing an equilibrium reaction here. So most of the time it's hydroxide, but sometimes it's the enolate ion. Okay, now because of the base strength of the hydroxide versus the enolate ion is a little more basic. So it's going to be in that equilibrium. Okay, once we have that enolate ion, it's stabilized by the fact that we can move these electrons back and forth. So we can have the negative charge on oxygen and the negative charge on the carbon. Okay, notice the oxygen here can act as a nucleophile, but the products it creates actually decompose and go back to making the carbon anion. So even though you do form it, it's not the reactive species in the set. Okay. So once you do that, these pictures are actually in backwards. So once you do that, you have your enolate ion is now your nucleophile, negative charge, nice nucleophile, comes in and attacks a neutral aldehyde. Okay, it attacks a neutral aldehyde because that is the partially positive carbon here is the best target. When it does that, it forms a new sigma bond right here, and the electrons are kicked up onto the oxygen, generating the oxygen anion. Okay, and the reaction stops here. Okay, notice it's in equilibrium here, which means it can break apart and form, but it's not going to continue on and do anything else until you add a proton to this anion. So the next step of the reaction is to add a proton by just adding water. Water is acidic enough to do that. And what we end up with is our final product is our beta hydroxy aldehyde plus hydroxide ion. Notice that we started with hydroxide ion. So it's kind of a base catalyzed system in the fact that we regenerate the hydroxide ion after protonation of the tetrahedral intermediate addition product. Okay, so this is our tetrahedral addition intermediate. Okay, so we see the 3 steps involved in the Aldol condensation. Enolate, forming a nucleophile. Attack of a nucleophile onto an electrophile, partially positive carbon, electrophile. Then that's an addition tetrahedral product that eventually will get a proton to give us our tetrahedral center where the carbonyl was attacked and maintains the carbonyl on the substrate that was the enolate. We're going to see that theme again and again and again. If you form the enolate, that's the one that's going to keep the carbonyl compound every time. All right, so questions on that? So this is, okay, the pictures are flipped, yes. The picture for step 3 is actually under step 2. The picture for step 2 is under step 3. Sorry about that. I keep saying I'm going to fix it, but I keep forgetting to do it. So maybe I'll do it this time. Okay, so that's the reaction with an aldehyde. Okay. Now, once we get that product here, now we have a beta hydroxy compound. Okay. Now, what do we know about dehydration to form conjugated double bonds? Well, we know that it's easy to form conjugated double bonds because they are more stable than isolated double bonds. So what we can do here is just by warming the reaction up with acid or base, imagine you did the reaction in base and you got to your hydroxide ketone compound, then you added acid to it to get your alcohol, and then you heated the reaction up. It would immediately lose water and create a double bond between that alpha carbon and that beta carbon. And it's really, really stable because now it's in conjugation with the double bond between the carbon and the oxygen. So that's why it really moves toward that product. Now, the other cool thing about it is this particular step is not reversible as readily. You have to really hit it with a whole bunch of excess of water to get it to do that. So this dehydration actually is really favored in the system. So when you have an aldol concentration, aldol reaction, where you add acid and heat at the end, you almost always dehydrate it to give that conjugated carbonyl double bond system. Okay, and we call these alpha beta unsaturated aldehydes and ketones. Okay, so it's we just gave it actually promotes that dehydration reaction. Okay. So so that can be interesting where you make it like that, and so you can take one reagent and have it attack another equivalent of the same thing. But what if you wanted to design it so they were actually different things? Well, we can do that. We can do what we call a crossed aldol condensation. It still uses an aldehyde or a ketone to generate our enolate. But the other component has no alpha hydrogens. Okay, so this is an example here. Notice there's no alpha carbon, so there's no alpha hydrogens. If there are no alpha hydrogens, that means this is the only species that forms a enolate ion. And the fact that you have this other carbonyl compound means if you put a whole bunch of base in here, formed a whole bunch of this all at once, the only thing it has to react with is the other compound. Okay. In this case here, the enolate reacts with this formaldehyde and creates a beta hydroxy ketone. Okay, so we started with a ketone, and then we had another carbonyl compound with no alpha hydrogens to create a beta hydroxy ketone. Okay, so what does that mean? Okay, that means that if we're really clever, we're going to choose something that does form an enolate. So we're going to use some compound that has alpha hydrogens. And maybe it's something that's unsymmetrical like an aldehyde that only has one kind of alpha hydrogen. Then we would add another reagent in the system that has no alpha hydrogens. And there's a couple different ways to do that. The first way is to actually just have no alpha carbons. That's an easy way to do it. Okay. The other way to do it is to have some kind of tertiary carbon next to the carbonyl. In this case, it's aromatic. In this case, it's also aromatic. But the key is you don't have a hydrogen there. Therefore, you cannot form your enol. And in this case here, we have an aliphatic one where we just have 3 methyl groups hanging off that carbon. And again, there's no hydrogen there, so it doesn't work. This is how we do a successful crossed aldol. One with alpha hydrogens, one with no alpha hydrogens, and you're going to get better yields on your system. Okay. So this would also work with diketones, by the way. Okay. So questions about the aldol and the crossed aldol. So the aldol is any aldehyde or ketone that ends up reacting with another one of itself. The cross aldol is something with alpha hydrogens that ends up attacking the thing without alpha hydrogens. Okay, and we know this to be true because the enolate is the one that maintains its carbonyl. The one that's being attacked is the one that turns into the alcohol. Okay, so okay, so that's kind of cool. What if you had 2 ketones on the same compound? Okay. Which one is it going to react? I mean, there's a bunch of different alpha hydrogens there. Well, there's a rule for that. Okay, so we call that an intramolecular aldol condensation. What that means is your compound has 2 aldehydes or ketones in it, and when it reacts, it'll form a ring. Okay, these happen really fast because it doesn't have to dissolve away into solution to find something to attack. All it has to do is use its random free motion to end up attacking itself. So these actually happen very quickly, but there's a rule. You typically only form 5 and 6 membered rings. Remember when we talked about 5 and 6 membered rings, those are the most thermodynamically stable rings. When you get to a 7, 8, 9 members ring, we have entropy. There's just too many modes of freedom, and it makes them very hard to make. 4 and 3 are too sterically demanding. They're too strained. So if you can make a 5 or 6 membered ring, then you can actually do that intramolecular aldol condensation. Now, the cool thing is you can find your product by figuring out which side which alpha hydrogen you play with. Okay, so let's consider this one right here. So because it's symmetrical, I'm only going to look at one half of it because we're only going to form the enolate on one half of the molecule. Okay, and so we have an alpha hydrogen here and we have an alpha hydrogen here. Okay, so that means we have, in theory, we can form enolate number 1 right here, or we can form enolate number 2 right here. Okay, which one's going to form? Okay, let's figure that out. So the rule is if you make either one of these can form, but the only one that's going to give us a product is the one that's going to give us a 5 or 6 membered ring. So let's see which one's going to give us a 5 or 6 membered ring. Okay, so we're going to start with that same compound again. And remember, we have alpha hydrogens here. We have an alpha hydrogen here and an alpha hydrogen here. So we're going to call this alpha hydrogen 1, and this is alpha hydrogen 2. Well, technically, I guess you call it 3 because it's on the 3 carbon of the chain. Okay, so let's start with forming the enolate on this alpha carbon 3, which is our second choice. Okay, so there's 2 alpha hydrogens there. If we deprotonate that alpha hydrogen, it's going to then attack the other carbonyl. Okay, so we have our negative charge here, and so it's going to attack this carbonyl. So when it does, we have a 1, 2, 3, 4, 5 carbons between those 2, which means that new sigma bond being formed is going to give us a 5-membered ring. So let's look at that. So this would give us, again, it's an equilibrium right here. And so when we do that, we can form a 5-membered ring. And then, because we're heating the reaction up a little bit, we can actually dehydrate the system, and we get to our 5-membered ring with a conjugated double bond. Okay. So what if we did it the other way? What if we got the one at the end here? So if we deprotonated one at the end here, that's going to be 1, 2, 3, 4, 5, 6, 7 carbons away from the carbonyl. So if it came by and attacked the carbonyl from that outside position, that 1 carbon position, we would end up with a 7-membered ring. And then, of course, it would dehydrate, giving us the most stable form of it, which would be this conjugated ketone right here. But it's not formed because it had to form a 7-membered ring. So if you can form a 6-membered ring, it doesn't matter which side you're taking that proton off. Whichever one forms a 5 or 6-membered ring is going to be your major product. Okay. So, but again, it follows all the other rules of aldols. It has to be an aldehyde or a ketone. You have to use a base. Most of the time, it's going to be in equilibrium. The first product you generate is going to be a beta hydroxy ketone or aldehyde. And then you can lose water to form a conjugated carbonyl double bond system. But notice when they lose water, they have to be conjugated. All right, questions about the aldol condensation. Make sure you write down those rules. It's that aldols are always aldehydes and ketones, and you always get the first intermediate you get as a hydroxy aldehyde or ketone, and then it can lose water. And it can do it within its own molecule if you have 2 ketones or 2 aldehydes. All right, so I've been harping on aldehydes and ketones. Is there other ways to form enolates? Well, yeah, we showed you on the table that you can form an enolate with an ester too, as long as there's an alpha hydrogen. So we call that a different type of compound. We call this a different thing. It's called a Claisen condensation. Okay, Claisen is something that only happens with esters. Okay, Claisen esters, and it's called a condensation because instead of forming an alcohol, instead of having a hydroxy compound on our final product, we actually lose one of the alcohols from the ester. Okay. Whenever we do this, we have what we call a beta keto. This is a beta here, ketoester, meaning we get a ketone and an ester in our products. Start with 2 esters, you get a ketone, an ester, and 1 equivalent alcohol. That's why it's a condensation. This kind of comes out of the reaction. Okay. So does everybody see how we get the name beta ketoester? This is our ester right here. And then this is our alpha position, and then this is our beta position, and that's where our ketone is. So this is the product you'll get from every Claisen condensation. Okay, so let's look at the mechanism. Okay, so the idea here is because we have esters, we can't do the reaction in water because the water will clip off the esters and give you a carboxylic acid, which is inactive to these kind of condensations. They do not form enolates. They'll just deprotonate the carboxylic acid and be done. So that means we have to do them in a solution that does not have water. Most of the time, we do it in the alcohol that we have the ester in. So notice here we have, we have an ethyl ester. We have an ethyl ester. We're going to do it in the ethanol with sodium ethoxide. If those were methyl esters, we would do it in methoxide, in methanol. Okay, we usually use the alcohol that the esters are made of. Okay, and that gives us a nice clean reaction. Okay, so again, our product for this is we form our enolate here. It attacks our carbonyl, and we get to an intermediate, but it does something different this time. Okay, so let's look at the mechanism. So just like before, the first step is the deprotonation of an alpha hydrogen. Now, we don't have a choice anymore because we have the ester on the other side, so we only have one choice for an alpha hydrogen. So that's makes it nice and simple, right? You deprotonate that to generate your enolate, which is of course stabilized by that equilibrium, by those two different resonance structures, right? Okay. Now we have a nucleophile again. So we have our nucleophile here that's going to attack another equivalent of the ester. So when it does that, in this case here, it's going to attack this carbonyl, and it's going to give us our new tetrahedral intermediate. And our new sigma bond, remember that sigma bond is those 2 electrons from our nucleophile, just like before, and we're going to generate this tetrahedral term. But this tetrahedral intermediate is different than the tetrahedral intermediate for the aldehyde or the aldol condensation. Because in the aldol condensation, we had hydrogen as a negative charge leaving or carbon as a negative charge leaving. Bad leaving groups. They don't leave, they stay. In this case, we have ethoxide as a leaving group. And the reaction's already in ethoxide. So it's a good leaving group for the system. So because of that, we actually can have the electrons from the anion tetrahedral form kick in and kick out ethoxide as our system. When it does that, it generates a ketone. So we made the enolate ion of an ester. It attacked another ester, but then it kicked out a part of an alcohol. When it did that, it gave us our beta keto ester. Okay? And then the next step that usually happens in the system is now that you have a dicarbonyl system, it actually deprotonates that center carbon. Notice that this is now our most acidic alpha hydrogen. And it's a good thing because when it deprotonates that, it protects it from further reaction. It stops there. That anion is kind of protected. The other ones are primary anions. This is a secondary anion. It's kind of it's sterically shielded so that it can sit there and wait to be acidified at the end of the reaction. Then the last step of the reaction is to protonate. Okay. And that gives us our final product, our beta keto ester. Okay, so why am I adding this step 4? Okay, that product we made, that beta keto ester, has a more acidic alpha hydrogen than our starting ester, which means it will be deprotonated, which means we have to have at least more than one equivalent of base to make sure the reaction continues to progress. Okay. So before I said if you had 2 aldehydes or 2 ketones, they could form a ring and do their own system and give us our ketone or hydroxyaldehyde. Okay, we can do the same thing with 2 esters in the system, but it has a different name. It's called the Dieckmann condensation. Okay, it's basically an intramolecular Claisen, but it has a special name. Okay, but just like before, we have to form a 5 or 6 membered ring. Okay, now unlike before, we only have a choice of one equivalent set of alpha hydrogens. We can only do it from here, and it can only attack this one here. So 1, 2, 3, 4, 5. Luckily, that would form a 5-membered ring. Okay? If it tried to form a 4 or a 7-membered ring, it wouldn't work. But if you have them spaced out, notice they are right here. They are 1, 2, 3, 4 carbons apart, which those 2 carbonyls are 4 carbons apart, which can make a 5-membered ring. If they were 5 carbons apart, that would make a 6-membered ring. Okay. So again, it's the exact same mechanism. You go through the tetrahedral intermediate, And then you deprotonate this one right here, stabilizing the system until you acidify at the end. Notice the water and HCl. Okay. Okay. Do we see why the Claisen condensation is different? It doesn't stop at the tetrahedral intermediate stage. It kicks out a condensate of alcohol, either ethanol or methanol. And then it creates our beta keto ester, which is then deprotonated because it's more acidic than our starting ester. Then at the end of the reaction, we protonate everything, and we end up with our product. Okay. All right. So do we understand the difference between aldol condensation, the Aldol reaction, and the Claisen condensation? Okay. So just like before, we have that intramolecular, but if we choose our ester and our target correctly, we can do what we call a cross Claisen. In a cross Claisen, you can use two different esters. But the key here is one of your esters has no alpha hydrogens. The other ester is the one that will form the enolate and create the nucleophile, and it's going to attack one of these species. So notice here we have the ester, but we have no alpha carbon. Here we have a diester. This is called diethyl carbonate, which means one of those ethyls will fall off right away. Here, we're going to attack one of this side and give us a different compound. And here we have no alpha hydrogens, but we still have esters. So just like before, the Claisen is only esters, but in the cross Claisen, one of our compounds has no alpha hydrogens. Now, what does that look like? So now if we had this species in solution and this species in solution, and we added methoxide, notice I changed the base there because we had the methyl esters of both of these. So we want to use the same alcohol as we have the ester. Okay, only one place on either of these molecules can be deprotonated, giving us our enolate here. Let me do that right. Our enolate here. So that means that is the one that has to come in and do the attack, which means this is the alcohol to leave, which means here we get our ketone on the species that's being attacked, and the species we made the enolate stays the ester. Okay, so that's the cross Claisen reaction. Still involves esters, and just like the other cross Aldol reaction, we have one species with no alpha hydrogens, and we have one species with alpha hydrogens. All right, questions on that? So you might want to make a table that says aldol, aldehydes, ketones, gives alpha hydroxy aldehyde or ketone, can dehydrate to form a conjugated one. The cross system, one does have alpha hydrogens, one doesn't. Intramolecular only forms 5 or 6 membered rings. And then do it again for the Claisen condensation, where you have esters giving off an equivalent of alcohol, giving you a beta keto ester every time. A straight chain or in a ring, and the cross Claisen has one without alpha hydrogens and one with. So make that into a table and get that all straight in your head. But notice they all use the same mechanism. Enolate, attack a carbonyl, find some intermediate, stabilize, and then get our final product in the end. All right, questions on that? Okay, 120, we got plenty. All right. All right. So in the previous chapters, we learned that base promoted hydrolysis, remember it's promoted because you need an entire equivalent of the base to make it do it, of esters upon acidification creates a carboxylic acid. When we do that same thing to our beta keto esters, we will end up with either a beta keto acid or a beta dicarboxylic acid if we have an ester on both sides. Okay. Now, once we have that, remember we had a reaction of carboxylic acids where if they had a beta carbonyl compound next to a carboxylic acid, that it would undergo decarbonylation because it could form a 6-membered ring. Okay, So let's look at that real quick. Okay. So in the case of our beta ketoester, again, all we did was deprotonate here and attack another equivalent at that same position to give us this after losing an equivalent of alcohol. Okay. So now we have this compound here. Okay. This compound here is nice and stable. It does not decarbonylate. However, if you clip off this here to turn it back into an OH, now we have that ability to form a 6-member intermediate, which looks something like, I don't show you. Okay, let me show the intermediate on the next slide. Okay, so we took our ester, we clipped off this. In this case, we're using base, so we had to use an entire equivalent of base, and we get the carboxylic acid here. Now, all we have to do at this point is heat it, okay? But drawing it here is a little what's the word? Not misgiving, not little deceptive, okay? Because if we redraw it such that the OH is up here and that carboxylic acid carbonyl is down here, now we have an opportunity to do a concerted reaction of decarbonylation. And so we have these electrons coming up to grab that hydrogen, these electrons coming down to form another carbonyl compound, and these electrons kicking out here to give us our new intermediate species. And that intermediate species is OH, and gives us our enol as our intermediate, which then, of course, rearranges to give us our ketone. But notice the step here loses CO2, and that goes off as a gas and therefore drives the reaction. Okay. So if you have it drawn like this, you can't quite see this 6-membered intermediate, that concerted reaction that allows for that easy removal of that carboxylic acid to give us the removal of CO2 and generate our ketone. All right, so we can use that strategy to build, let's say we had a couple esters and we wanted to make this big ketone out of it instead. We can use this strategy of decarbonylation to end up with our final product the way we want. Okay, so what if we actually wanted this product as our final product? Okay, and we could start with this carboxylic acid here, and well, that's okay, but that would give us this part of this component here, but we need to have somehow to add this part of the component here, and it's probably another carboxylic acid, right? Oh, what's the other crazy thing here is that if we turn this into our ester, there's no alpha hydrogens, right? So what does that mean our reaction is? Is it a Claisen? Is it an aldol? Is it a cross Claisen, a cross aldol? Which reaction do we have to use this substrate to make this product? Go ahead and type in the chat room. Proves to me somebody's awake. Although it's a nice sunny day, I'm sure we're all awake. We have a substrate with no alpha carbons. With no alpha hydrogens. That means it has to be some kind of cross reaction. And we're going to use an ester, so that means it has to be a cross Claisen. Exactly right. Okay, but the reason we also know it's a cross Claisen is that this side does not look like this side. So now we have to back out what our other ester looks like. And we know that this portion here, this side of it here, has to be the one that we form the enolate of, because we can't form an enolate here. All right, so let's design that. Let me move to actually the blank pad. All right. Okay, so we want to oops, that's not right. So we want to design that with a cross Claisen, and we have to use that carboxylic acid as that benzoic acid as one of the compounds here. So let's draw what we have to start with again. So we have to start with this. And our final product looks like this right there, okay? Later. All right, so if that's like that, let's take a look. Oh no, remind me later. All right, so let's try to back out from our product what we had to have. So because we started with esters and we ended up with a ketone, that means we had to do a decarbonylation. So if we had to do decarbonylation, our step one away from this one has to be something like this. So if this is our final product here, that means we had to have something that looked like OH right here. Let me erase this. To do that decarbonylation step, right? But to have this on here, we still have to have all of this structure here. So it's going to be, okay. So do we see how this structure, when we decarbonylate it, right here, it gives us this structure here. Okay. All I did was figure out where the carboxylic acid had to be to do the decarbonylation. That's important because that's going to tell us what to use as our ester to start with to form our enolate. Okay, so if that reaction had to be there, if this has to be one of the starting materials, I'm sorry, if we had to make this before we could make the final product, that means that the enolate has to be on this carbon here, right? Because we had to attack this carbonyl to get to this product here. So that means that our starting material, this has to look like, there has to be some kind of ester. I'm just going to use ethyl here. 1 and 2. So this is the alpha hydrogen we need to make this move on. So that means this is one of the starting materials we had to have to get to this final product. Let's see, is that right? Wait, no, there's one extra carbon here somewhere. Let's see, there's this, there has to be a methyl group here, and then there's that, and then, okay, there we go. Okay, so this has to be the intermediate we need to get to here. And so we have to make our Claisen happen here, which makes our starting material look like this. And that makes this the alpha hydrogen we're going to have to depropionate. Okay. So then to actually make this work, we're going to have to turn this into the ester. So we're going to use the ethyl ester. So now let's take this product here and see if we did it right. OET. And we're going to do OET here, 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 here. and that methyl group there, and this hydrogen here. Okay, so we only have one alpha hydrogen. Did we do it right? Okay, first step, deprotonate, give us our anion, which would give us here. Second step, attack of the carbonyl compound to give us there. That product is going to look like this, O minus, OET, and there's going to be carboxylic acid hanging off here, a bridge here, and this here. So that's going to be our intermediate. And then when this kicks in, it's going to kick that out here, giving us this compound here. And then it'll decarbonylate to give us that. Okay. So now that you have the product, you can actually now go stepwise backwards and figure out which materials you have to start with as well. That's actually called retrosynthesis, and it's something that's very difficult, but that's probably the only one I think we do this semester. Okay. So let's go back up to there. So there we go. So what we have here is we have to determine first where the carboxylic acid had to be from the decarbonylation. And once we have that, we can back up to what the intermediate looked like. We can back up with a tetrahedral intermediate like that. That would give us the two things we have to start with to make it happen. Okay? Do we see that? How we can back it up by knowing which bonds we're making and which bonds we're breaking. All right, so let's tie this into a little bit of biology right here. We actually use this kind of system a lot in what we call the acetyl coenzyme A. This kind of reaction, the Aldol condensation, Claisen interaction works really well in the system. We can do it with both esters and thioesters in the different little systems, and it's used a lot in biological systems. So if you think about the pH in a biological system, pH in the biological system usually hovers right around 7.8. So these have to be equilibrium reactions that are constantly making and breaking these bonds to continuously create new and more complex molecules for our body to run on. Okay, so let's look how that would go. So in this case here, we have the acetyl coenzyme A right here. And so this is the part hanging off here. And so we can actually deprotonate at this site here to give us an aldol material. Then this deprotonated system can attack this carbonyl, giving us our keto ester. So you see how we're getting a ketone here, but we still have this ester associated with the coenzyme A. So this is what we call an acetyl coenzyme A. And it kicks out one equivalent of the coenzyme A as the alcohol component. Okay. Now, the cool thing about it is now this creates a nice acidic proton, which then can react with other things, and it can go through this enzyme to clip that off and generate another carboxylic acid group here. And so this is the gluteryl coenzyme A ester, and this actually makes it really very usable in a different metabolic pathway. But the other cool thing is it's very regiospecific because we use an enzyme and it only gives us the S isomer on this alcohol. Okay, so we took that ketone, added across it with another compound in another Claisen reaction, Aldol reaction, to give us our beta hydroxy esters. So we did a Claisen and an aldol, and we're making power for ourselves. All right. So then we can clip off the coenzyme A at the very end of this here and use that to give us this carboxylic acid diol. I don't know what that does. I'll have to look that one up. Sorry, I don't remember. All right, questions on the importance of the Aldol and Claisen condensations. Again, write that table up. Aldols, aldehydes, and ketones produces an hydroxyaldehyde or hydroxyketone that can lose water to form a conjugated system. Claisen always involves esters and typically produces a ketoester unless you decarbonylate, and then it creates only a ketone. All right, and oh, that's what it's used for. Okay, it's used for APT to create the phosphonates. That's what it's used for. I didn't know that. I'll have to look that up. Okay, we can also use the same kind of intermediate to generate things that'll give us statins or blood pressure lowering medications. In this case here, so that is probably Lipitor. Statin, yeah, it is a statin drug. It affects liver function. Okay, so I kind of want to stop here today. We're a little early, but I would definitely spend about 5 minutes writing down the requirements, the inputs and outputs of each of these reactions to help get it straight in your head. Okay, that's going to really help you look at it. And then when you go to the homework, you'll see that some things will just give you a product and ask you which reaction had to happen. And so if it has an OH on it, you know it had to be an aldehyde or a ketone. It was an aldol reaction. If it ends up with an ester, carboxylic acid, or just a ketone, you know it had to be a Claisen. But you really need to get the starting materials and products straight in your head. And I think a nice little table is the best way to do that. Okay, any questions? Okay, what I'm going to do is I'm going to go ahead and stop recording, and so you can ask questions freely.